In this video, we're going to take a look at the Even More Density Problems worksheet for Advanced Science. It's based on some of the labs that we've done in class, as well as just some review of density calculations using unit multipliers. The first question is similar to the thickness of aluminum foil experiment that we did, but instead of aluminum we have copper. We're told that we have a sheet of copper metal foil in a triangular shape. We can see the three sides of the triangle are given in feet, and we know the mass is 15.26 grams. We can look up the density of copper. The density is 8.92 grams per cubic centimeter according to the periodic table that I've got right here. Your booklet in your lab manual may have a slightly different value, but it should be pretty close to that. The question here is broken down into steps. So we want to find the area of the triangular foil, then we'll find the volume, and then we'll find the thickness of the foil. So first, the area. This is a little bit of a math problem because we know the three sides of the triangle, but not the height. There's a couple of options. One would be, like we mentioned in class, there is a formula actually called Heron's formula. Heron's formula for area of a triangle. It says that the area is equal to the square root of S times S minus A, S minus B, and S minus C, all multiplied, where S is called the semi-perimeter, meaning it's half of the perimeter of the triangle, so A plus B plus C divided by 2. So Heron's formula is very useful for finding area of a triangle when you know the three sides like this. Alternatively, because this triangle is an isosceles triangle, two sides here are the same, we could drop down the height like that, and in an isosceles triangle, the height of the triangle would bisect the base. So if this base was 1.22 feet, the height bisects that, so it cuts it in half, so this would be 0.61 feet here. And now we can look at that right triangle that we've created, and we could use Pythagoras to find the height of the triangle. I'm going to jump in and use Heron's formula instead. So Heron's formula says that the area is the square root of, now let's quickly find the semi-perimeter for this triangle. S will equal 1.75 plus 1.75 plus 1.22 divided by 2, so half of the perimeter. 1.75 times 2 plus 1.22 is 4.72, and divide that in half. So S is 2.36 feet. So now the area would be 2.36 times 2.36 minus 1.75 times 2.36 minus 1.75 times 2.36 minus 1.22 equals, now I'll just do all that on the calculator, so square root, bracket opens on my calculator, 2.36 times, open a bracket, 2.36 minus 1.75 times again, open a bracket, 2.36 minus 1.75, close that bracket, times again, open a bracket, 2.36 minus 1.22, and my final answer is that the area of this triangle works out rather nicely to be 1.00 square feet. That's kind of surprising, actually, that it works out so nicely. If you had done it the other way around, if you had found the height first, maybe I'll do that up here at the top of the page for those of you who did that, Pythagoras would have said leg squared plus leg squared is the hypotenuse squared. Square of the two legs equals the square of the hypotenuse in a right triangle. So we would say 0.61 squared plus h squared is 1.75 squared. So h squared would be 1.75 squared. Take away 0.61 squared. Grab my calculator. 1.75 squared minus 0.61 squared is 2.69. Therefore, h is the square root of 2.69, which is 1.64 feet. So there's the height of the triangle, and now we can find the area using our formula base times height divided by 2, so or 1/2 base times height. Let's see if we get the same answer as with Heron's formula. 1/2 times the base, 1.64, the base here, although it doesn't really matter what order we multiply. The base was 1.22, and the height is 1.64. These, of course, are all feet. So 0.5 times 1.22 times 1.64, and not surprisingly, we get the same answer, 1.00 square feet. So either using Pythagoras to find the height, and then the traditional area of a triangle, 1/2 base times height, or using Heron's formula, we get the same answer for area of this triangle. Now, this answer is in square feet. The answer wanted it in square centimeters, the question rather, in square centimeters. So I'm going to take my answer in square feet. I'm going to use 4 unit multipliers. Because it's squared, I'm going to switch from feet to inches, and again, feet to inches. So now my square feet are gone, and I've got square inches. And then get rid of the inches and switch to centimeters. And do that twice because we wanted square centimeters, right? So the inches cancel, and we're left with square centimeters. There's 12 inches in a foot, 12 inches in a foot. There's 2.54 centimeters in 1 inch. There's 2.54 centimeters in 1 inch. So on the calculator, 12 times 12 times 2.54 times 2.54 times 1 up front, we get 929 square centimeters. Okay? Now I'm keeping 3 significant digits here. I think that's right. Actually, looking in here, we might actually have rounded off to 2 sig figs instead of 3, but we're allowed to be within 1, so this is a pretty good answer. Alright, part B says what's the volume of the foil, and it says refer to the back of your solubility chart. The solubility chart is in your science booklet. Let me just see if I've got mine convenient here. So this is our solubility chart. There are the solubility curves on that chart, and in the back, page 116 in our books, there's a list of densities. And if we look at copper 8.92 grams per cubic centimeter, which is what I had on my periodic table. So that's why we wanted to look there to get the density of copper, 8.92 grams per cubic centimeter. Alright, so if we know the mass of the foil, up here we've got a mass of 15.26 grams, and we have the density of the foil, we know that we can find the volume, and we know the density will be a unit multiplier to do that. So let's take our mass, 15.26 grams. We'll set up the unit multiplier using density to get rid of grams and switch to cubic centimeters, the volume. The density was 8.92 grams for every cubic centimeter. So now we can say 15.26 divided by 8.92, 1.71 cubic centimeters. And finally, we can figure out the thickness of this foil, because we know that the basic thing is like a excuse me, it's like a rectangular triangular prism where we have area of a base and height. So volume is area times height. Area of the triangle times the thickness, the height, will give us the volume. So we can find the height or the thickness. Don't confuse this height with the height over here of the triangle. Those are different things. This height is the thickness of the foil, will equal the volume of the foil divided by the area of the foil. The volume we just found was 1.71 cubic centimeters. The area we found in part A was 929 square centimeters. And notice I can tell from the units that I've set that up properly. Cubic centimeter divided by square centimeter will give me centimeters, which is the unit for thickness or height. So 1.71 divided by 929. This foil has a thickness of 0.00184 centimeters. All right. Question number 2 is more of a straightforward density problem. A student needs 25.0 grams of methanol, only has a graduated cylinder, so what volume of alcohol should she obtain? We are given the density of the methanol, 0.789 grams per milliliter. So this is really just a question where we're given a mass of methanol, and we want to know what volume of methanol, and we're going to use density as the unit multiplier. So it's very similar to what we did back in part B above. So we'll take the 25.0 grams of methanol, we'll use the density to get rid of grams, and convert to milliliters. The density was 0.789 grams per milliliter. So now 25 divided by 0.789. The student should measure out 31.7 milliliters of alcohol. Part 3, question 3, is similar to a lab we did to find density of a liquid. We put an empty graduated cylinder on the electronic balance and we have its mass here in grams. We put some liquid in the cylinder and recorded the mass again, this time the cylinder with the liquid, 163.01 grams. So we can tell already that if we subtract those, we'll know the mass of the liquid. And then we have the volume of the liquid here, 63.8 milliliters, so we can go find density. So let's start by finding mass of liquid. And it's a very good idea to put these little labels down, not just jump in and start doing calculations. The mass of the liquid will be the 163.01 grams, the mass of the cylinder with the liquid, minus 112.74 grams, the mass of just the cylinder. And when I subtract that, I'll know the mass of liquid. So 163.01 minus 112.74, there's 50.27 grams of liquid. Now remember, when subtracting or adding, we round off our answers by the number of decimal places, which is why I kept 2 decimal places there, because each of those had 2 decimal places. Now we're going to find density. When finding density, this is the only time I really want to see the density formula, mass divided by volume. So mass of the liquid, 50.27 grams, divided by volume of the liquid, 63.8 milliliters. The data sheet above said milliliters. So the significant digits, 4 digits divided by 3 digits. I'm going to round this off to 3 digits. So 50.27 divided by 63.8, 0.788 grams per milliliter. Okay? Very close, by coincidence, to the density of the methanol that we saw back in question 2. Question number 4 the last question on the sheet, part A and B. We've got an aluminum cylinder. So right away I'm thinking volume of a cylinder, the formula. We know its diameter and we know its height. So part A, we want the volume. So you might want to sketch a picture. You don't have to, but the height was 10.4 centimeters and the diameter was 2.46 centimeters. So the radius would be half of this. So R equals 2.46 divided by 2, 1.23 centimeters. Alright, and this is the height. So volume of a cylinder is pi r squared, the area of the circular base, times the height. So equals pi times 1.23 centimeters squared times 10.4 centimeters. Notice that some people would have made a mistake of simply putting 2.46 as the radius, even though the question says diameter. That's partly because they're not reading the question carefully, but notice by drawing that picture on the side, it just made it a little bit harder to make that mistake, because I've shown in my picture that the 2.46 is a diameter. That reminded me I'm going to need radius, so we converted right away to radius. So 3.14, or the pi button on your calculator, times 1.23 squared times 10.4. The volume is 49.4, keeping 3 significant digits, cubic centimeters. Now this cylinder was made of aluminum, and if we look on the back of the solubility charts again in our science booklets, we know the density of aluminum is 2.70 grams per cubic centimeter. So what is the mass of the cylinder? Well, to do that, we'll just take our volume, 49.4 cubic centimeters, and we'll use that density again as a unit multiplier. So we'll get rid of the cubic centimeters, and we'll switch to grams. 2.70 grams per cubic centimeter, so 49.4 times 2.7. And the calculator says 133.38 grams. However, we're only supposed to keep 3 significant digits, so we'll say 133 grams is the mass of the aluminum cylinder. So there's some practice, density problems. Notice the use of unit multipliers to solve the density problems. Okay, that's what I want to see in your answers. Notice that my work is very neat. I've got all the units shown. I've got formulas shown where appropriate. So that's the quality of the work that I want to see on tests and in your assignments.